Hello everyone. Now we continue the second model. Okay, show how can we write in question form. This is developed an EOQ model with constant demand and constant iteration. Okay, so as we do in first model, there are some assumptions and some notations. So first we write some assumptions. So from this we have two assumptions. First one is demand is constant and second one is iteration is constant. So first we can write the demand rate is constant. Okay, second one is the iteration rate is constant. Third assumptions will be lead time is 0. And fourth assumptions will be shortages are not allowed. So these are the assumptions for this model. Now we write the notations. So first notation will be, we can write D for demand. So D denote the demand rate. Now the second one, theta. This is the deterioration rate. You can write rate of deterioration. Okay, and its value is always lies between 0 and 1. Okay, if there is no deterioration means the value of theta is 1. If fully deterioration then it may be 1, and 4 means if deterioration rate is 20%, so you can write 0.2, and if it is 2% then you can write 0.02 like that. Okay, so it may be vary from 0 to 1. Now since we have an order model, so Q denote the order quantity, and the next one, there is some inventory level in a particular time interval t, in the particular time t. So it may, we can write it is the inventory level at time t. Okay, now there are some costs. So first we write C1 as ordering cost, and second we write C2 as holding cost. This is per order, and C2 is holding cost per unit time. Okay. Now there is one more cost which is related to deterioration. So C3 is deterioration cost. per unit time. Okay, and the last one, T, which is cycle length. So first step is write the assumption, second step is write the notations. Now we move to third step, which is mathematical modeling. I hope it is clear to you. So we go for the next step, which is mathematical modeling. So first we draw the graph. Here axis denote the cycle length, that is time. Here we can say cycle length. And y-axis denote the inventory level. Okay, we can denote it by IT. Now since this is a order model, suppose the order quantity is this. So here inventory level is depleted due to the joint effect of demand and deterioration. So it curve may not be flat, so it will be like that. Okay. And this is due to demand and deterioration. Okay. So for the modeling part, we will convert it into mathematical model. So how can we write? This is the inventory level, and we see that this decrease means there is a rate of change in inventory, and this is because of due to demand and deterioration. So how we can write it? DIT upon DT equal minus D, since it is decreasing, so that's why minus sign is here. So minus D, and how much inventory will be deteriorated. The total inventory level is IT, and this theta is the rate of inventory level. Rate of deterioration means how much inventory is deteriorated. So we can write it like that: D of IT upon DT plus theta IT equals minus D. Now it becomes linear in IT, so we can solve it by usual method. Means first we find the integrating factor, which is equal to e to the power theta dt. So it will come e to the power theta t. Now its solution will be it times e to the power theta t equals minus d e to the power theta t plus um, one constant of integration. So it will become it e to the power theta t equals minus d to the power theta t upon theta plus c. Okay, one more thing. This is for interval 0 to t. Now boundary condition is also here. So we can write boundary condition. From this figure, it is clear that at time 0, the inventory level is 0, means I0, sorry, inventory level is Q. So I0 is Q, and at time T, inventory level becomes 0. So I of T equals 0. So to find the value of C, we apply the boundary condition. So now at T equals T, so IT is 0. So from this we get 0 equals minus d e to the power theta t upon theta plus c. So this implies that c equals d e to the power theta t upon theta. Okay. So now we put the value of c here. So we get it e to the power theta t equals minus d e to the power theta t upon theta plus d e to the power theta t upon theta. Now we can divide it by theta t e to the power theta t. So we get we can take d by theta as a common. So we get e to the power theta capital T minus small t minus 1. So this is the inventory level in the interval 0 to t. Now we find the order quantity. So here we get it equals d upon theta e to the power theta t minus 1. Okay. So now the order quantity will be by using the first boundary condition that I0 will be Q. Okay. So it will come Q equals d upon theta e to the power theta t minus 1. So this is our order quantity. Now there are some inventory cost. So I'm writing here inventory cost. So inventory costs. So first one is ordering cost. Okay. So ordering cost is C1. The second cost is holding cost. Holding cost is calculated as C2. This is the per unit cost for holding, and in the inventory is hold in the duration of 0 to t. So the limit will be 0 to t. Okay. So 0 to t it dt. So now it becomes C2, and we can put the value of it here. So this will come d by theta e to the power theta t minus 1 dt. Okay. Now we can easily show. So it will come C2 d upon theta, and we can easily integrate it. So we get e to the power theta t minus t of minus theta. Okay. Minus t. So this will come holding cost equals, after solving it we get C2 d upon theta, and when we apply the upper limit then it will become e to the power 0 upon theta, and when we apply the lower limit then we get e to the power theta t upon theta, and also from here this is minus t and plus 0. So holding cost become C2d upon theta. We can take theta as common, so it will become theta square, and it can be written as e to the power theta t minus 1. So this is the holding cost. Now we calculate the deterioration cost. So deterioration cost is calculated as the rate of per unit, rate of deterioration per unit cost for deterioration, and 0 to t theta times it dt. If we see here holding cost and deterioration, there is a little bit difference. Here is only multiply with theta. So there is no need to find the deterioration cost, just put the value of holding cost and multiply it by theta. So it will come C2 d theta upon theta square e to the power theta t minus theta t minus 1. Okay. Now the total cost. So total cost will be ordering cost plus holding cost plus deteriorating cost. So we can write TC equals C1 plus, we can write it like that, C2 d upon theta square e to the power theta t minus theta t minus 1 plus C3 d theta upon theta square e to the power theta t minus theta t minus 1. Okay, so now it becomes C1 plus, we can take, uh, we can write it like that, C2 plus C3 theta d upon theta square into e to the power theta t minus theta t minus 1. So this is the total cost. Now we find the total average cost. So now total average cost become just divided by t. So it will come C1 by t plus C2 plus C3 theta d upon theta 2t into e to the power theta t minus theta t minus 1. Okay, sure. Now we go for next. So here we go, total average cost is C1 upon T plus C2 plus theta C3 upon, this is D theta square T and e to the power theta T minus theta T minus 1. Now we can expand it because we have to find the value of T here. So ATC equals C1 upon T plus C2 plus theta C3 d upon theta square T, and we can write it like that, 1 plus theta T plus theta square T square plus and so on. We can neglect the higher terms. So now it will become this one, ATC equals C1 upon T plus C2 plus theta C3 d upon theta square T into theta square T square. So it can be written as it is equal C1 upon T plus C2 plus theta C3 d upon into T upon theta square. Okay. Now since this is the total cost, so our aim is to minimize the total. Okay. So as we know, to minimize the function, because it is a cost function and we all know that to minimize any function, if it is in single variable, then the rule is that maximum minimum principle first differentiated with respect to that variable and put equal to 0 and find the value of that, and then find the second derivative. If it is greater than 0, then that is minimum. So same rule is applied for this. So now for the maxima and minima, we calculate d of AT c upon dt, means we differentiate this with respect to t. So we get minus c1 upon t square plus c2 plus theta c3 d upon theta square. Okay. Now to find the value of t, just put this equal to 0, means d of atc upon dt equal 0. So this become minus c1 upon t square plus c2 plus theta c3 d upon theta square equals 0. So this implies c1 upon t square plus c2 plus theta c3 d upon theta square equals 0. Okay, this is with equal sign. Okay, and this is not. So from here, theta square is cancelled out here because this is cancelled out. So it becomes t square equals c1 upon c2 plus theta c3. So the value of t will be square root of c1 upon c2 plus theta c3. Now to check whether it is maxima or minima, we find the second derivative. So d2atc upon dt square. So this will come on 2 by 2c1 by t cube. And we all know the cost is always positive and time is also positive. So this will be greater than 0. Means the total cost is minimum and our optimal value is this. So this is the complete model. Okay, thank you.